All right. Hello. Welcome to the Off by One security stream. First one of June. We've got Mr. Chris Lopez this week. Chris reached out and was like, hey, you don't do enough Mac stuff. It needs to give Mac some love. And I was like, you are damn right on that one. So we were just talking before the stream. Like, I live out in the Bay Area, and I would say like half the shops out here are either Mac only or Linux only or whatever. So definitely excited about this one. I've never honestly done any reverse engineering of malware in ARM or on macOS at all. So I'm going to learn a lot on this one. So thank you, Chris, for coming on. If you want to give a little background about yourself, I'm sure folks would love to hear about it.
Yeah, so a little bit about me. Let me see. Started in IT prior to getting into security. I was in a SOC for a while, 2 different SOCs, mostly Windows shops to start out. Then I moved into a SOC that was all Apple, and I never touched the Mac until I got there. Like, they sent me that Mac like my first day, and I was like, I don't even know how to use this thing. And I had to somehow be in a SOC and protect these devices. So then I went down a rabbit hole, and I got really interested in Macs and IR related to Macs and malware related to Macs. And now I'm a security researcher, and that's all I do is reverse engineer Apple Silicon and all that fun stuff. And yeah, it's been really great.
That's awesome. Yeah, it's funny. You made me laugh there because I got a Mac that exact same way. I was like, well, I don't know how to use this thing. I was like trying to fight using Parallel or something to try to run a different operating system. But eventually I gave in and learned to love it. And then I do music. So like on the music world, it's like all Mac for the most part. So that's good stuff.
Yeah, so, you should have seen my Google searches when I got that. Like, how do I do this? What do I do for that? And I didn't know anything about the Mac. So it was really cool to learn.
That's an important thing you said there, though. I think that people need to hear, especially new to the industry, is you started in IT. Exactly the same thing for me. Exactly the same thing for like literally everybody I know who's been doing this for a while. I know, like, obviously over the last 10 years, security's, before that even, but blown up. And it is a path to go straight into security from university or from, Starbucks barista, wherever you're coming from, which is totally fine. But I've heard from a lot of people like, hey, the job hunt for someone who's new right now, it can be a bit of a struggle. So I just, encourage folks, don't be afraid to go take an IT position. You'll learn so much about the business, about the systems you're going to be protecting once you make that switch over into security. So plenty of time to do that.
Yeah, the fundamentals really helped out. I was also told when I started, there was no route for me to get into security. It was like, oh, you're just going to be in IT. Like, you just stay there. It's fine. But it ended up working out. I actually started messing around with security, like, getting my own VMs and trying to hack and all that stuff as like a hobby. And then I got super interested in it. And I was like, oh, I really want to do this. And then that's kind of what drove that whole thing to get into it.
Nice. Yeah, I was at Computer Science Corporation, and I was doing network security engineering, and I was like, I want to make the jump fully into security. They're like, no, we need you to stay there. I'm like, I'm going to leave. If you don't switch me, I'm going to leave. Like, and they liked me. And the manager was just like, no, I can't do it right now. So I just quit.
Yeah.
And found a job pretty easily. And jobs were made.
Yeah. Funny thing about that. So when I was told it wasn't possible, I looked online, using Outlook, and I found like the manager of the SOC at our company, and I paid for a flight and I just went out there, and I'm like, hey, I want to do this. What do I do? And he gave me, luckily, like a roadmap. It wasn't quick, and I still had to, learn a bunch of stuff to get in, but you definitely should not listen when people tell you, nah, that's not possible.
Yeah, you got to shoot your shot, man. That's what's funny. You remind me a similar thing I did. I was working at a bank, and I just really wanted to learn how to just get bigger in my career. And so I just went up to the CIO one day. Like, it's a pretty intimidating thing for me to do at this large company. I was like, hey, excuse me, sir. I was like, say, hey, is there an opportunity to sit down and have coffee with you? I just really want to learn how to develop my career, and just you inspire me. And he took me up. He's like, I'll take you out to lunch. Like, here's my PA. And I hit that person up, and we set it up. And that was, again, another great decision. So not that that's what we're talking about here, but these are some pretty good job tips, by the way. So don't be afraid. But as usual, I encourage you to ask questions. Chris is here, and I'm excited to learn what he has to share. So please do so. But I guess, I'll ask a question. I got to check Discord to see what questions have come in there too. But you can post them here in the chat on YouTube or LinkedIn. I don't think Twitter shows up here, but I'll take a look there as well. But I guess what are some? Have you done reverse engineering of Windows malware or only Mac?
So when I first saw someone open up IDA, right? I was very early in my SOC journey, right? They showed me all this Intel stuff, which looks kind of ugly. And I was like, no, I don't want to do that. It wasn't until I started, looking at Macs that then I started actually reverse engineering malware. So I've gone the other way. I started looking at Windows stuff after the fact because there's some really interesting techniques and things that are happening on that side. But yeah, I started with just Mac malware.
I was going to ask about this. So somebody who has done malware of like all the operating systems and said that Windows can be the most complex, and that when he does reversing on other operating systems, malware specimens, that they tend not to be as, I guess, intricate. Have you found it to be the same or totally different?
I think they're just different. There are some really advanced things that I've seen on Windows malware that I have not seen that level of complexity on like macOS specific malware. That's why I think that for anyone that's interested in diving in to malware reverse engineering, I think like Mac malware is a really good start for that specifically, because now I'm seeing things and people in the field too, that things are adding, like there's more complexity coming as more adoption of Macs and more people are monitoring Mac devices. I think that the malware authors are having to adapt to that as well. Windows has had a long time of that for things to get better when it comes to the techniques that they're using. Yeah, I think it's just we're going to keep getting there with Mac malware.
Yeah, that makes sense. Like, when you go back to the early days of exploit development, I mean, things just weren't as complex because they didn't need to be. And then as things get more complicated or the mitigation start coming in, things start getting more technical, more complex. So yeah, I imagine that makes perfect sense. Non-operation asks, what are some common macOS malware samples you would suggest a beginner to reverse engineer?
Okay, so I'm going to have to put a plug in here for Patrick Wardle and his Objective-C GitHub. Got to find the link to put in here. He has a repository of a bunch of Mac malware that you can download without having to have, virus total and all that fun stuff. And he has a corresponding blog, and that's how I learned personally. I didn't know anything, and I spent, I think, $50 on like a Hopper disassembler license, and which is great, like super awesome start. And then I just went to Patrick Wardle's blog. I looked at all his blog posts, and I just went one by one downloading the sample and just like almost like using training wheels, but in a good way. Like I was having one screen, having his blog up, and the other screen looking at a disassembler and just kind of like learning how to do it. But yeah, that's kind of, I say there's a lot of really interesting ones recently that have been coming out. Info stealers, which we're going to be talking about, are kind of like being talked about a lot more recently, which is cool. There's a lot of those. Some samples that don't have, a lot of obfuscation would be cool to look at, just so that you can get comfortable with, the art of actually reversing something before you dive into having to use scripts to, deobfuscate code and all that fun stuff. But check out that website, Objective-C, where there's a bunch of blog posts for old samples and newer samples too.
Yeah, I'll get that posted up here in a moment.
Yeah.
What's the most common malware type you're seeing? Are you seeing a lot of ransomware? Like what kind of stuff are you seeing?
No. So ransomware, no, because of the way that Apple has certain protections in place, like something for people that are not familiar with the side of, Apple security. We have things like SIP, system integrity protection, which protects certain directories from being able to be modified. So ransomware would be really difficult to cause a lot of damage to the actual OS. So we don't see a lot of samples related to that. There was something recently, I believe it was Lockbit had something that ran on macOS, and it would target specific directories to encrypt. But what we're mostly seeing right now is a bunch of info stealers and spyware-like samples, and that's what we're going to be covering today as well. Some of these info stealers.
Sweet. That's the more common stuff you're seeing these days.
Yeah. Especially this last year, it's kind of blown up. I guess people. Unfortunately, there's a lot of cracked apps and things like that. Google ad poisoning that leads to software that looks legitimate, but it ends up being backdoored and having a stealer element to it. That's kind of what we've been seeing a lot on macOS recently.
Interesting. If someone's asking about, have you seen a lot of gatekeeper bypasses?
Well, it's not really a bypass. But a lot of these, so because of the Apple protections in place, like Gatekeeper, which checks and verifies when you actually run something, it gives you that prompt. Are you sure you want to run this and all that fun stuff? So there are a lot of these malware authors that are still instructing users to it's not a bypass, but it's more so just run it. Like you can just accept the risk and run it. Because a lot of these samples are ad hoc signed, which we'll get into later, just meaning like they don't actually have like an actual signature from a developer ID attached to the sample. So they wouldn't run properly unless you enable that to run. So that's kind of what people talk about when it comes to bypasses. There have been some vulnerabilities in the last couple of years related to that. I think there was one that may have been related to that the last couple of years that was actually leveraged by malware, but not recently. So yeah, to answer that question in a much smaller way, we've seen a lot of these malware authors still using these prompter like, hey, just click on this and just allow this to run. And that's kind of what people consider to be like a bypass.
Yeah, user bypass, right?
Yeah.
Layer 7 or whatever. Hey, layer 8, sorry.
Yeah.
So I think I haven't honestly done too much research in the malware space or even the exploit dev space in Mac OS, just because it's its own real thing. I mean, I did a deep dive into Blast Door bypass because I had a friend who discovered a vulnerability and kind of pulled me into that. So I got to learn a ton that way. But it's hard to kind of jump over to another operating system and just, I mean, it's not hard. I guess it just takes time, right, to do that.
Yeah.
Someone's asking, a couple of people are asking what the GitHub link you mentioned was. I think I missed it. What was the GitHub link?
So I believe you posted under the malware.
Yeah.
Yeah, because that leads you to a GitHub page.
Oh, okay. Back up.
That's what I meant. Let me see if I can find it really quickly.
Yeah, so that link here that I posted will take you to the page, Chris says. I can.
Oh, I guess they have it. They have it here. Oh yeah, malware collection on GitHub. Here, let me put this. What's the best way of sharing this on here?
Just put it in the comments, or
okay.
I'll just post it out.
Yeah, so that's if you want to just grab the whole thing off GitHub.
Yeah, you're correct, Raj. Apple has done an amazing job with security over the years. I wish their patch process was a little bit more, like Microsoft's, but can't have everything. Let me grab that link. So copy that, and I'm going to add that into the comments so it's there forever. And then
I think the link that you posted does have that link there, but this is just a direct one to the GitHub page. Anyone wants to just grab it, grab the whole thing.
Well, I know you got a lot of stuff to share, so I don't want to, chat for too long. But let me, let's put your screen up, and then let you get started. And I'll look at the questions. If the questions kind of fall in line with what you're doing, I'll just interject. But otherwise, we can save the questions towards the end. But again, don't feel bad asking questions.
Awesome. Let's do this. All right. You can see that we're good. Good to go.
We are good. Yep.
All right. So we're going to be using a lot of the terminal here in the beginning just to kind of walk through some of the application structures and things that are very macOS specific, just to make sure everyone's on the same page as we start diving deeper into this. I have this picture up of this cat. That's going to be the first sample we look at. And this is written in Swift UI. So that's like a replacement for Objective-C, if anyone is familiar with that on the Apple side of things.
I can't see that image hearing that song from that damn, you know.
So it's like the first thing I saw when I ran this in the debugger and it popped up, I was like, oh my goodness, this is awesome. So we're gonna start there. Just wanted to pull that up because it's hilarious. I'm gonna be doing just all static analysis here. There's not going to be any debugging or anything like that. That's why I got a screenshot of it versus running it and showing that. The reason I bring this up is because I want to spend a little bit of time talking about Swift UI. That's not something I see talked about from a reverse engineering perspective often. And it is incredibly not the most enjoyable thing to reverse engineer, is the best way that I can say that, because of UI elements and closures and all this stuff on top of just beautiful C. So we're going to just start there. I have this directory here that I have some of these things that we're going to be looking at today. And this is just a list of stuff to make sure I keep myself in the right direction as we continue. Okay, so there are two different types of files that we're going to be looking at. The first one here is going to be a .dmg file, which is what this is at the top. So that's a disk image. We can just take a look at that really quick. I don't think we're going to get any real information about it. So zlib, compressed data. So the way that you can actually look at this without running it is you can use a command called HDI util attach. And the reason that we're going to do this is because we want to see what the contents inside of this disk are. So then we can start looking at, the actual application structure. So we're going to attach that. Cool. It has been attached, and this is what it is. This is another one of those cracked apps, or one of these that does something it says it's going to do, but it doesn't. So it tricks the user into actually installing this and running it. So we're going to navigate to that directory. Mission control. I'm just gonna be okay. So we have three different things within this directory, this volume. So we have the activator app that we're going to be looking at, and then we have what's like a link to the applications directory. And when you run a disk image, it asks you if you want to move a file over. So you move the directory over, and that's why there's a link in this directory here. This mission control app, essentially for this malware, what it does is it actually patches this application, like it cracks it. We're not going to focus on that functionality of it. We're going to worry about this activator.app and what it does. So applications on macOS are essentially directories. You can see that here. If you look at this activator.app, you'll see that it's a directory. So you go inside of this directory to actually get to the binary, and you can get a bunch of information about, what the structure of this app is and what resources it pulls from in order to, for example, show this picture and all that stuff. So we're just going to start there. Can you see all the way in the bottom here? Let me just.
Yes. Yeah, I took us out of the picture.
All right. Let me just move this over. Let's make it nicer. Okay. So inside of this, you have the contents directory, inside of this .app folder. Then you get into what you actually want to look at. So the binary for these applications is always going to be inside of the macOS folder, inside of these .app folders. But we're going to look at resources right now because there's going to be an interesting file in there that we're going to see later. And this is where I got very excited when I was first looking at this. So I forgot what version it was. If you don't have Xcode installed, now I could be wrong, so please correct me if you're in the chat. I So macOS no longer is installed with Python after a certain version. So this was really interesting because it actually has a Python installer inside of the application. So I was like, yes, this is probably really interesting to look at. So we have a couple things in here. We have this app icon and things like that. That's just what the app looks like. So we're not worried about that. And then we have, if we can see clearly here, we have this tool, which is a binary. So on macOS, we have what's called universal binaries. So as Apple moved away from Intel, they started packaging their applications into a universal binary. So essentially, this one binary has two slices in it, which is the x86 64 slice and the ARM 64 slice inside of this one binary. There's tools that you can use that come with macOS that you can actually remove a specific slice. Oh, hold on.
Computer disappeared.
Yeah, so because I was connected to my machine, all right, because I was connected to my machine for another machine, that machine went to sleep and it expected this machine to be asleep for some reason. Okay, so universal binaries, two architectures. We're going to be focusing on the ARM 64 slice because it's awesome. And so let's just start from there. That's going to be a file that we're going to look at.
Your screen's not there still.
Oh, let me share screen. I got to do it one more time. Sorry about that.
No worries.
All right. Good?
We are good.
Awesome. Okay. Yes. Universal binaries. Cool. So let's go back. We're going to come back to this tool later. This tool is important. This tool binary is important. So inside of here, we have, like I said, that macOS folder. So let's go in here. This GUI is going to be the first binary that we're going to analyze. So we can see this is another universal binary. So it has ARM and x86 within the binary. And we can get some information about this file using a utility called CodeSign. So this gives you some information about, like, for example, the signature, if it is signed. So if we look at this, we see right here, ad hoc, and right here, the signature showing that it's ad hoc signed. So that means it's not actually signed using a legit like team identifier. This is signed. This can be easily signed with the command line or just when you create something with Xcode. So this won't run without being prompted to run usually, and that's why these malware authors, they employ the prompt technique to be like, allow this to run, please, and trick users into actually running it. So that's just some signature information. So now let's start seeing some other command line tools that we can use to understand this sample a little bit more before we dive in super deep. So another cool tool is called Old Tool. And this gives us information about linked libraries that this sample uses. So this helps with understanding some of the capabilities around this sample before you start looking at things in a disassembler. So a couple things that jump out, we see some Objective-C is used in here. We see this was written with the AppKit framework. We see SwiftUI, which I mentioned already. So there's some SwiftUI stuff in here, which is expected since it's going to be this GUI app that's back there, that cat. We see that this also links in a security framework. So maybe it's using some of those APIs as well. And you can just get a good idea of some of the functionality that this sample has. Cool. So that's like some triage to get you at least acquainted with the sample before you dive headfirst into it. All right, so let's now actually take a look at it. So I'm just going to copy this out of here just to make it easy for me. Malware, and then, okay, cool. And I'll let's take a look at it. So I'm going to open up Binary Ninja, which is my favorite disassembler as of late.
It's very clean.
Yeah, it's so good. It's so good.
Yeah, when I had Jordan Wines on not too long ago in a stream, I learned so much about the tool. I was like, damn, it's almost making me switch from IDA, and that's pretty impressive.
Yeah, it's so good. Like, it's just, I come from Hopper, so my experience, it's like been such a big jump, at least for me, from like what I can do and like the scripting and all that fun stuff. It's been really awesome. So I have the binary ninja database file, which is what's created when you actually open it. But I just want to show the GUI really quick because this one has a bunch of my already edits and stuff like that. I just kind of want to walk through some of the functionality here. Okay. So Swift UI is really complex, at least to me. Maybe the folks that spend more time with Swift UI, this is a lot easier. For me, it is very difficult to read when it comes to its disassembled state. Now, it's nice to write. It's difficult to read when it's in disassembly form. So just a couple things about it. So in Swift UI, you have this concept of like your content view, which is how things are shown on the app that the user sees. And within there, you have certain members of this content view struct that you can then add like an image to it. So the main body of the app, you can add an image like this activator image, this cat. And then you also can implement something like a button, which is what this patch is. So that's what I first did when I was looking at this, is how I want to answer what happens when I touch this button, when I click this patch button. How does that work? So that's what we're going to kind of walk through a little bit here. So we're going to cheat a little bit because we don't want to spend all the time I spent on this before trying to figure this out. We can look for a initialization of this button, and we can see here that it accepts two arguments. We have the action and the label. So the label is going to be the name of this button, and the action is going to be what happens when you actually click on this button. So let's see how that works. So we now see that it basically just calls this, but we want to know what actually calls this initialization, right? So we go from this symbol and we look at the cross references to it, and we see that it's inside. Now here's where it gets like unnecessarily complicated. We have this function is closure one in closure one inside of content view.body.getter. Awesome. So here goes the initialization of this button. And if we go and we look ahead, so we got to talk a little bit about ARM now before we get to this function call. So some ARM fundamentals. So this instruction that you see here, this BL instruction, this branch and link, this is like an Intel world call. We're calling this function, right? And that's going to be the button.init method here. So the way that things are passed to functions in ARM is through registers, right? So instead of passing things through the stack, we have examples of that in ARM2. The way that this usually works is x0 is equal to the first argument, right? x0. Then we have x1, x2, x3, and we pass in here. So for this example, we should have button, if I can spell, button, action, and then label. So this action should appear in x0. This label should appear in x1. Now things get a little bit weird when it comes to these higher level languages, but that's what you'll see a lot in C. Different languages also use methods differently, and we'll see that in Objective-C a little bit. But essentially, that's how you pass values to functions, is you pass them through registers. So you start at x0, x1, x2, x3, until you get to x7. And if there's any more arguments inside that function, one, I'm sorry, because that's a really annoying function to have to reverse engineer. Everything else is passed through the stack after X7. Cool. So we see the initialization of this button. Now we're going to click around a little bit because we need to understand how this is created.
There's some folks in the comments looking at this and saying, wait, this isn't x86. Do you have any good recommendations for folks to learn ARM and pick it up quickly?
Azaria's book is like what I consider the Bible on that. I've read it a few times because the first 2 times I really sucked at it, and I had to like learn. I had to read it again to try to actually understand it. Her book's amazing. There's some more content on that I can share as well.
Cool.
But yeah, so great question, because it is a lot when that's how I feel when I look at Intel stuff. So I get it. I'm like, oh no, I don't want to look at that. So, all right, let's click around a little bit. We see that this call, so this instruction is interesting. So let's talk about these 2 instructions a little bit. This ADRP and this add instruction. So ADRP is loading a pointer from this page. And this add instruction, what it does is it adds this value to this value that you got, and then it puts that value into X2. So this ends up, this address, if you put those together, so 0x1 0000 5 EFC, no, EFC, like that. If you go to that, this is where our closure is. So all this is doing is it's adding these values to this address, and it's putting that into X2, which is going to be this address. So that's what this instruction does. It puts those together in order to calculate this memory location, and then it saves that into the X2 register. So inside of here, we see the button that we wanted to see before. So this is that patch button. Here is how it's set up. And we have a call to a string.init method, which passes in, it looks like 1, 2, 3 different arguments. So the first argument is going to be this. So we move 5 into W8. We move that into X1. And that's going to be passed in as the UTF-8, like the length of this string. W2 is going to be if it is ASCII, and that's going to be a yes. So it's basically creating this string, and it's initializing that string. This might actually look a little bit better if we were to look at this in the pseudocode. So these are those values that we're passing in, the patch, the length of this, and if it is an ASCII. So this is the UTF code unit count. So that's going to create and set up our patch button label for this button that we're creating. So if we go back, we are inside of, let me go here because of how it's actually not the prettiest thing to look at.
A quick question. Anonymous is asking, is it possible to patch the button so the text says meow instead of patch?
Anything is possible.
No, but in what language is a binary written? Someone's asking.
This is in Swift UI.
Right. Okay.
Or cool. Swift. Yeah, this is all Swift, so it's a little bit ugly, I'll be honest. Okay, so this is going to be for the text label for button. Now, if we look at this closure over here, we'll see, I gotta go really quickly to find where it is, because I believe it's inside closure 1 and then content view in it. I just gotta find this really quick. We need to find, just so that I don't spend all the time on this, we're gonna initialize something that's called start job. So this gets called from this initializer, and this is going to be the action that is ran when the button is clicked. So let's start from there. We have the start job.main, and this is going to run this start job.main function. And this is going to be what we're going to be looking at and trying to understand. And we're going to switch our thinking caps over to Objective-C. So Objective-C is pretty interesting. I know it was a pretty big pivot, but just for time's sake, we have methods that are passed in by functions or passed to objects with this Objective-C message send function. So what this is doing here is, first, we are getting this main bundle string into X1. We already got this class reference into X0, and this returns itself. So X0 has the class. X1 has this main bundle string. And then we're going to end up having to run. So what that does, hold on, just to explain this one really quickly, because it's going to look a little ugly for people that haven't seen this before. So Objective-C, you have an object like NS bundle, and we're passing in main bundle as our argument or a method for NS bundle. NS bundle is an X0, and our string, which is our selector in this case, is main bundle. And it's going to return the main bundle for this application. So the way that it looks like this is NS bundle, and then X1 is our selector for main bundle. Once those things are set up, you'll see that we call this Objective-C message send. So Objective-C message send is really important for Objective-C built binaries. What this does is it actually runs that method against that object and returns whatever is supposed to be returned there. So we can see here, return values are stored in X0 when a function is executed. So that value is then stored onto the stack here. And we see this NS bundle main bundle, which I edited. Okay, so the next thing that we're going to do is we're going to do that same ADRP to get a pointer and then add one hex 100 to it. And this is going to be this tool string inside of the C string section that's then loaded into X0. And we're going to create a string using what we saw before for that button. So we have the length of the string here in 0x4, and we're saying that it's ASCII. This is an X2. So then we're creating that string, and we can see that here. String init, this is the tool string. We have our main bundle. Now we're going to continue. So the next thing that it does is it runs this NS bundle main bundle path for resource of type tool, and we have this NS string that we created, which is over here. So what this does is it returns the path to this tool. Now, what is that? If we go back and we go, this is why we looked at this before. Our tool binary is here. So what this did was it created a path to that tool so it can use that. So how does it use that? Well, there's a bunch of stuff here that we're not going to get into. We have the path for tool. This is some error handling to see if it was 0 or not. And we're going to just save that for later. So now we have this object that we can use for the path to this tool binary, and we'll use it later. The next thing it does is it creates another one of these strings, string.init. And you're going to see this a lot if you look at Swift and Objective-C binaries. There's a lot of Objective-C in Swift binaries. So this is a Swift method, string.init, to actually create this Swift string of this Python package. And then you're going to see string.bridge to Objective-C. This creates an NS string of that Swift string. There's a lot of that when it comes to the way that these different languages work together. So we have another one of these strings that we've created. And now we bridge there, string bridge to Objective C. We have our package file. And here's what's going to happen here. This is another function so that we can create another target. That's what it's doing. It's creating targets to these files that are inside of the resources directory, inside of the app application bundle. So same thing, NS bundle, main bundle, which is the method that's run against the NS bundle class. And we're passing in this argument, path for resource of type, and we're getting the resource, this file of type package. If we look here, that's what this is. So if we look at this, this is able to determine that this is a package file. So now we have our target to that package file. Awesome. So there's more stuff that happens here, and we're going to get into how it uses this in just a moment. So there's different types between a string and a URL when it comes to Objective-C in this case. So you can change a string to an URL, and a URL in this case is just a path to that file. So that's what happens here. We do another string init. Oh, sorry, right here. URL init, file URL with path. We're running this method against this object. URL for the package path for the Python package. And then we're creating a string here for a temp Python package that we're looking at. And then that's going to be used in order to copy item at URL to URL. So all this is doing, we have our object for the path to this resource inside of the application bundle. Now we've created another object that has temp in name so that we can then copy the item from the resources directory into the temporary directory. And that's what happens here. We use the default manager, and we use this method copy item at URL. We pass in the package path in bundle to this, and we copy that over. So this is the return value for that copy item return. And then it does some error handling to make sure that it actually works. Cool. So this moved the Python package inside of here to the temporary directory once it runs. Awesome. So the next thing that it does is like, this is where I think it gets really, really cool. So we have this elevate object here. And when I first saw this, I didn't really understand the way that this worked at all. We see that we have the type metadata accessor for elevate. So it gets metadata about this object, and it allocates this object here, elevate, cool. And then we have this tool file here, and we're creating a pointer to this tool. And I didn't really understand what that meant. And then this is what happens. So this ends up running the run method against this elevate object, and it passed in the value of tool. How do you know that? This is tool. It's passed into x2. X2 is going to be the argument that you pass in to this run method. Run is an x1, and the object, the elevate object, is an x0. So, so we're passing in like this. Just to explain this, because this is important to understand what happens next. So x0 is elevate object. x1 is our selector, which is a string. Selector, which is the run method. And then we have x2 is going to be the argument that we're going to pass to this method. And that is our path to tool. So tool x2, run is an x1. We're loading that in this value right here. And x0 has our elevate object. So when we run this Objective-C message send, it executes this. Here's what's interesting. This doesn't give you a branch that you can just click on and go to how this works. You then have to look this up inside of the symbols. Here it is. So it's like, I guess that can be considered like an indirect call. I don't know. But essentially, it's just setting up this call. Now we come here. Here's where I think this is really cool and it gets really interesting. So we know that X2 is that tool object. It gets moved around, and let's see what happens. So pointer to the tool object, it checks to make sure it's actually there. And then it creates a C string to that pointer to tool object path, and it runs this. Authorization execute with privileges. We pass in the tool path. And what this does is it actually prompts the user. For anyone that's used Mac devices before, you'll get that prompt basically asking you for your credentials if you want to run this application that is for higher privileges. This is APIs in the security framework for Apple that it leveraged in order to have you execute the tool binary with elevated privileges, with root privileges. So that's what this does. You can actually look this up. For anyone that doesn't know about this stuff, because I definitely don't know all of this stuff, spend a lot of my time. Oh, and this is deprecated now. But spend a lot of my time just looking at Apple documentation about what these functions are. So definitely did not know what that meant before I looked at this. So a nice Google search for that function tells you what it is, and then you can look at how this works and like understand what this does. Runs an executable tool with root privileges. And the funny thing about these malware authors is they actually called it tool. I don't know if that was on purpose, but maybe it was a copy paste on their side just to make it easy, but they called the file tool. So this runs with root privileges. So it's able to do more than just a regular user. Awesome. So now we know that this application ends up running this other application, this other binary with elevated privileges. So in order for us to continue, we need to actually look at this file now, because now the chain is like added one layer to this sample. Okay, so this just makes it easy for me to remember where things are because I lose track of stuff. Cool. Open. And now we're going to look at this tool binary. The only way that this is going to actually run is if the user actually input their credentials. And then we get to see things that happen after the fact.
Is there any particular like reason or trick that folks are using to trick the user into actually falling for that? Or is it just, I mean, is it common that people are just so like, oh yeah, sure, I'll enter my credentials?
This is going to maybe sound a little mean. It's not meant to sound mean. A lot of Mac users have gotten used to these prompts. It's just that every time you're doing something, there's a prompt, you put in your credentials. We've kind of been trained to put in our credentials for stuff. And using that API that we just talked about, that legit API, even though it's deprecated, it's still a legit API. That prompt that comes up is going to look super legit. Like it's not going to look like a fabricated API at all. It's going to be what we're accustomed to seeing.
It's just like when Vista came out and UAC was kind of over the top, and then they fixed it with the Service Pack 1, but it was too late for Vista.
Yeah. It's interesting. We've gotten trained now to put our passwords. So attackers leverage this. And the fact that they use this legitimate API just makes it more believable that it's legit.
Well, since that one's deprecated, the newer way of doing it, is that any harder for someone to do?
No idea. I haven't looked at what the replacement of that is. That would be interesting.
It said some service manager or something. I can't remember. I saw something on the screen.
Yeah. Let's see. It probably tells you what it was replaced by.
Yeah, right there. Launch D and service management framework.
Oh, yeah. Okay. Yeah. For like legitimate apps, you use this helper tool that runs with elevated privileges, and that's managed by LaunchD. That's how legit applications do that. Yeah, so you don't even have to prompt the user for that in order to run it. But that's part of like the installation of certain tools. So yeah, that does make sense. that's how you should do this. But this is still available, so it would work. Okay, so we've changed a little bit here. Now we're looking at a whole other binary that was executed with elevated privileges, and we're going to just kind of talk about this a little bit because we want to move on to some other stuff. Luckily, this is not stripped. It gives you all of the names of the functions that it runs. I mean, all this stuff. I mean, I was really happy when I saw this because I knew that I was not going to spend a bunch of time having to name all these things. It kind of tells you what these things are, which is awesome. We start in the main function, and let's just kind of look at this really quickly. So we are setting, this is going to be, just to do some edits real quick, default manager is going to be that if exists that path, and this is going to be a class reference. So this is not telling me what string it's actually looking at. For anyone that wants to look into Objective-C code in Binary Ninja, there's an amazing plugin for this. So I ran that plugin here, analyze structures, and these are references to core foundation strings. So if we double click on this, we'll see that this is referencing user local bin Python 3. So we can start getting an idea of what this might be attempting to do, because there's a huge if statement here that is going to pass in this default manager, which is like how the file manager object works. And we're passing in file existed path, and this is going to return a bool if it exists, and it passes in this value. So it's checking to see if Python 3 is on the system. And it does that for the homebrew Python. It does that for the op local bin Python and user bin Python. And you can just click on these and see which ones they are. This is inside of the CF strings section. Cool. So this is a check to see if Python does not exist. So if it does not exist, then you install Python. Now that makes sense. So it just goes and looks for Python and installs it. So it does this sudo installer. So it actually runs this. I don't know why they pass in sudo when they already had root privileges, but whatever. It runs the installer application, and it targets that temp Python package file that we talked about before. And this was moved into temp by the previous binary. So this is an example of the previous binary setting things up for this binary to do what it needs to do. And then it runs that and installs Python. Cool. So then it does this command here. So we create this NS string with the string with format, and we pass in this spctl master disable. So this disables gatekeeper. So that's interesting as well. Then it does count apps and path, and it basically just checks for number of applications that are installed. So this does a bunch of stuff after, and what ends up happening is it installs a bunch of Python scripts, and that's where most of the functionality of this is. But this was all using this patch binary that looks like it's legit to crack this other application. So a user will download this so that they can, I don't know, for some reason, crack this other app. And it has this hidden functionality in order to run this other application with root privileges, which installs Python on your machine. If it's not already installed, then downloads a bunch of Python scripts and runs Python scripts. That's kind of like the summary of this specific one. There's a lot of stuff there. Cool. Let's talk about the next thing. We're going to talk about Cuckoo. So this one was a pretty exciting one. This is another sample. And let me just show you what that looks like. So clear. This one was reported by us over at Kanji. Adam and I. Adam found it, and he was gracious enough to have me take a look at it. And we looked at it together and started reversing, and it ended up being something really fun. And it took me forever. I spent a couple days reversing this one because of its obfuscation, which we'll get into in a moment. I think it'll be fun to show it. But let's start from all the way from the beginning. So we have another DMG, this Cuckoo V1 DMG. So we're going to go back so that I can talk about it. Okay, so we're going to do the same thing. HDI util attach. We're going to attach this disk image. This is a common way that users or that malware authors deliver malware, these DMG files, but it's also a legitimate means to also deliver a legit app. Like when you download Google, it's brought in a DMG. So they're just leveraging existing tools. So here goes the file that we're going to look at now. Volumes, dump, media, Spotify, music converter. So this malware attempts to disguise itself as this Spotify music converter. So my understanding of this, because I have not used this ever before, it looks like it may connect to Spotify and allow you to download music from Spotify that then you can use. I don't know. I'm not sure. I didn't look at how it's used legitimately. But let's go take a look at that folder structure. So that was dump media. And then here, let's look at this one. Okay, so we have this application. Now, you can also run code sign against this application here. And this one's also ad hoc signed. Does give you some more information as well if you want to look at this. We also see the identifier, just upd.upd. Not sure it was named that way when they were creating it. Okay, so let's go into this application bundle. So it's going to have the same structure we talked about before, contents and all that fun stuff. I always like looking in the resources directory just to see if there's anything that stands out. And something does stand out. This is another dump media, Spotify music converter. Not sure why there's another application inside of this application, but if we do code sign, just to show you one that looks different, dump, we'll see that this is actually a legit signature for, I mean, I don't know if it's legit, but it is signed with a team ID. So this is different than the ad hoc sign one. So it's possible that this application inside of this other application is the legitimate application. And this is a sample that's disguising itself as that application. Cool. So now when I was looking at this initially, I already started getting suspicious because that's interesting. Why would it do that? And in order to make sure we have time to look at this, we're not going to look at this file brand new. We're going to look at my analysis of this file because it took forever. We're going to talk about some cool things that it does. So let me just open up this. Awesome. Here we go. So let's start all the way at the top. Here you can press G. I think that's the same thing in IDA, and go to an address. Start. There's a lot here. This also uses some obfuscation, which made this very difficult to analyze. And I can show an example of that in a moment. But let's talk about some of the functionality that this does. So let's explain this and why. Oh, and all of the symbols were stripped. So this was all my renaming to try to make sense of this. And it's still more in here to look at. So we're loading in a pointer to this address. We're moving in that pointer to this address into X0, which is the first argument that's going to be passed into this grab UUID. So this is just zeros. I renamed it UUID because you're going to see what it does in a moment. That's the first thing that it does. It does this. So this grab UUID function, this is how the routine for the XORing works. It's not super it looks a lot more complicated than it is. It just took a while, at least for me, to understand it. But basically, what ends up happening is you have your encoded string, which is here. I already changed it, so it's no longer encoded. You pass that into a register, you load values from there, and you end up loading in the key from another memory address, and it ends up XORing at the end of this. So we go and we XOR through all this, and then it just goes one by one, XORing. This is where the XOR happens right here. And after that, once that string has been de-XORed or XORed back to its actual string, then it just passes it as a value to, as an argument to this popen cmd, which I renamed to that, which then runs the popen function in order to basically run that command. Awesome. And for anyone that's not familiar with that, popen, right? So this opens a process, and it expects a command passed in as a string, and then a mode passed in as a string as well. So that's why you see at the very top, this is going to be the string that's passed in, and then we have that R as the argument. X0 is the command, and that command, you can see that it's not changed here. So X0 is still that command, and then it runs, it passes in that R to X1, and then popen is run. So popen would look like this, just to reiterate the ARM stuff. Popen X0, X1. So it would look like popen command string, and then it passed in R. So each one of these commands that this sample runs, which you can see what this does, this, if anyone is familiar with macOS stuff, you'll see that this is for the system profiler command, and you can actually see that better in a disassembly. And it looks at the hardware data type. This is what it runs here. And I can just run this to show you what the output of this would be. This returns my UUID. So then what ends up happening after this, just to not have to go through all of it right now, the address that was passed in to the grab UUID, which was here, this was passed in. So this is the, we can just change this if we want to, address to UUID. This then gets used and written to after. So then what ends up happening is this address to UUID, we can see that it then gets used everywhere. And this is how it sends this UUID in its communication outbound as it collects more data. You can see in the cross-references all the times that this is loaded for different functions that are called. Okay, so that's the first thing it does. Now let's look at some other things that it does that are pretty interesting as well. So after it does that, then it does this thing. So what this ends up doing is it decodes this string, and it then checks against this string down here, just to show how it's used here. And it ends up checking the lang get environment against this. So when you run that, just to show, because this is getting that get env, so it's printing out the lang here for the system. So you can echo lang. This is what my system has. It then checks against all of these, which are different countries. And you can make out some of these. It was hard for me. I had to Google some of these, but this looks like Russia. And that ends up being something that it checks against to see if it wants to continue running. So it checks to see if you're not in one of those countries. And if you're not, then it runs. If you are, it terminates. So we can see that in this if statement. If we follow this if statement, it opens the legit converter. This ends up running that one that's in the resources directory. So that's pretty interesting. So let's talk about some of the stealer stuff that it does here. Since this is a stealer, what does it do? So we can go into save password to file. And just to walk through this a little bit, it ends up creating this password.dat file, and it ends up querying the user for their password. And the way that it does that is using this password capture function. This runs an OSA script command, which is here. This is the prompt box that a lot of macOS users have been warned to be very careful with, because this does not look like that legit one that we were talking about before. This is one of those that look like it was just made by somebody, but people still fall for it. This is display dialog, and this is what it says. This macOS needs to access system settings, and then it prompts you for your password. This is a very common way that stealers have captured passwords. So again, all this stuff was encoded. It then uses this key to decode it, and then it passes that to the popen function, and then it gets the text return from that call, which is the password, and then it saves that password. And it saves that password in this password.dat file. So we've touched on this a little bit, but I want to show an example of how, yes.
In terms of obfuscation, that's a pretty easy one, you think, or medium, or what do you think?
For me, I don't have a lot of experience with obfuscation. I've been getting a lot more recently because a lot of these stealers are coming with more and more of it, which has been really cool to learn. It took me a bit because usually I've been used to the XOR key being 1 byte in length, but this is multiple bytes in length. And I didn't understand that you can just put all those together and just make it a rolling XOR Python call, and it's fine. So it took me a little bit of time. But eventually, funny thing, the way that I figured out how it worked was I had to use a debugger and go instruction by instruction to understand how it worked.
Yeah, exactly.
And it was after that, then all of them use that same key. So then it becomes very easy. And I'll show, so this is called here. So let's see where this is. So then I can talk about how we decode these strings, because I think that would be interesting to people to understand. So the way that the decoding works here most of the time is there is a XOR function, I renamed it that passes in two things, the encoded string and the length of the string. And it passes it to this XOR function, it grabs that key, and it XORs it, right? Simple enough. So luckily, we can use snippets for that. And let me just get the snippet editor up. And let me get an example of this.
I have no idea why balloons just went across the screen, but that was interesting.
On my side?
Yeah, on your side.
Holy crap! I don't know. Well, because we're at the main event here. Excellent. That's why. Okay. So thankfully, a friend of mine helped me with this. I'm not the best Python scripting person. I've been having to learn a lot of it recently because of Binary Ninja, which is a good thing. But I got some assistance on this and just kind of tailored it to this specific sample. And you can create these snippets for yourself, but you can also just run this in the Python interpreter in Binary Ninja if you want to, which is also really cool. You can just run that right here. So let me just clear that. We're going to paste this. This is going to be our string. Our key is this value here. Just move this up a little bit if we can. And we're going to pass in the address and the length. So the address that this encoded string starts, and the way that we know that it starts here, you got to do some ARM stuff. We'll see a reference to it getting loaded into X8. And the way that this works is we load a pair of registers. We're using these Q registers, these vector registers, in order to load values from within this memory address. So it loads these values, these two registers with 128 bits from here, and then it stores those at this address, right? So this is on the stack, x29 minus 0x70 hex. So this gets stored on the stack. That's why I renamed it to encoded string, because that's what it is. And then it just keeps going from there until it gets to all of the bytes that were referenced by this address have been loaded and moved into the stack. So this is a really important thing to talk about with ARM. ARM is a load and store architecture. So this happens a lot in contrast to some of the Intel stuff, where you actually have to go and load something to actually do something with it, and then you store it back. Load something, load a piece of it, do something with it, store it back. So that's what happens.
It's interesting that it chooses a stack to do that, but I guess maybe it's a speed thing instead of having to allocate heap memory or something like that, but pretty cool.
Yeah. I don't know why it wouldn't use the heap. Maybe did it use malloc here? No. Yeah, so you'll see that a lot. And the way that you know that it's on the stack is because of x29 being a register, the frame pointer that points to the quote unquote bottom of the stack. We subtract, when we're subtracting, it's in between the frame pointer and the stack pointer. And that's going to be the space that was allocated to this function. And all that happens in the function prologue up here, where we allocate certain bytes to the stack pointer, and then we set our frame pointer, and then we create our stack frame for this function. And then we can see the calculations of that are inside of those brackets. What those brackets mean is the memory address that is the calculation of x29, which is our frame pointer, minus 0x70. And then we just keep going as we get all the bytes from here, because it is a pretty big number. The 0x4e are a pretty long string. And then we pass it to this XOR function. So let's do that. So when we go here, we're going to get this address. I just created this variable to try to make my life easier. And then we pass in the length. So 0x4e. And if we run this, this is a command that's output by this. And what's really cool, you can also make this a lot more convenient, which is what I did, is you can actually write to the binary the results of this XORing. And this is another really cool feature in Binary Ninja that I love, the fact that you can write back to the binary itself. So I'm going to just show that really quickly because I think it's really awesome. Let's get this. I clicked on an address, so it went back. And then 0x4e. Now, this has unfortunately crashed on me because I was doing this too much, but it should be fine. All right, so we have the same things, right? The only thing that changed was I'm using this bv.write, and it writes the result, which is the whatever the result of this XORing, to the address that I passed in. And as long as everything works, it should write it, and it did, and bam. That is how I went through each one of these strings, because I was not able to create an automation to do it all because of how it leverages this XOR function, and it passes in these two values. It was hard to script it because it wasn't just one byte. And yeah, probably someone out there can figure out a way to script this a lot easier. I had to go one by one. So that's an example of how this XORing works for this sample. Yeah, and you can see, sorry, what was that?
I said it's really interesting. It's cool. It's good. So you're explaining things very well. So thank you.
Oh, awesome. It's a lot, and I try to like not speak too much. I can do this all day. All right. So something that it does that's really cool is it uses. I love this topic. Variadic functions, right? So functions that can have a variable amount of of arguments that can be passed to them. So funny thing about this, I don't know how many people have looked into this, but the most common C function that everyone uses is a variadic function. The way that you know that is because we have these 3 dots here that symbolize that we can have a variable length of arguments that are passed, right?
Yeah.
So this function uses a family of this printf in order to save values that are then used later. And we're going to walk through one of those examples because it's really cool and it kind of contradicts the way that ARM passes arguments to functions. Okay, so here goes an example. So we just did this XORing and this returned that string. So I'm talking about this one specifically just to make sure that we're on the same page. So the way that I know where this ends up is before all this happened, we stored all the encoded strings. We stored it on the stack. So I renamed this value to be the output of this XORing because that's what's going to be on that stack. And this happens throughout all of these samples. And then we have these sprintf functions that combine strings together. So this is how it works. sprintf, it might be easier to see it like this. So we have the UUID, the local.uuid file path, and then we have this %s.local-%s. So what this ends up doing is it ends up running this, just to show it. Man, s printf. Right here. sprintf. We have our format that we use, and we actually are more concerned with the result, where things are returned. So as strings are combined, in this case, we use those formatters like the %s for a string that is combined and it's returned in x0. x0 is going to be the value that this string, once combined, returns to, and then we can rename it like that. So let's look at an example of that. So sprintf is getting called. We have the UUID that we had before, the x0. We're moving that into x. Oh, sorry, it's here. We're moving x8, this UUID. So let's talk about this one by one. UUID in x8. And then we're returning from this get env home. So that's the same thing for anyone that's familiar with like Unix stuff. You can just do this echo home and it returns your home directory. That is the return of this function right here. So x0 contains our home directory, which is why I put home env and UUID right here. And in order to pass these values to the sprintf function, you actually have to pass them on the stack. And how do you know that you're passing it on the stack? You're using this STP instruction. So that's for store pair of registers. So we're storing x0, which is that string for our home directory, and x8, which is our UUID, and we're storing that on the stack.
See, it's more like AT&T syntax that people hate. You know, those of us who use the Intel syntax, it's like, wait, why is it going that direction?
Yeah.
There's some cool commands though. Like I love some of the assembly instructions, how ARM does it versus x86. So it's cool.
Yeah, to be fair, only the store instructions move left to right.
Oh, okay.
Everything else goes the normal way. This is abnormal for ARM too. I don't know. Maybe the designers were like, oh, we're moving it this way, so let's just make it so that it does that. I don't know. Those are the only ones that do that. It's the STR and the STP. So don't be scared away from ARM. It's beautiful. Don't worry. It's not like AT&T.
Same with periodic functions. I'm like, wait, you mean runtime polymorphism? Like, oh, C++ background. Sorry, let's go.
Yeah, no, not there yet. C++ is also a nightmare to reverse engineer, honestly. Okay, so we have these stored on the stack, and then we're going to load. We're going to add this value to SP, and that's going to be this is our string that we're going to use, and we're moving that into X21, and we're adding that same value here. This is a pointer to what's going to result from this function being called. And then we subtract X29 by this, which gives us our .local string again, .s, which is going to be the value that's passed into X2. So the way that this looks, actually it'll be better here. sprintf return value, which is, that's an address. And then we have this is going to be the actual string right here that we are going to use, which is our function, which is our formatter for this call. And then we have the home environment string, and we have the UUID. And when this is called, return, which is also X0, which is pointing to that, is going to be the home directory /.local -UUID. So it combines the home directory and the UUID of the machine into one, and it creates this string with the sprintf function. And this is used throughout this sample a lot. So that's one example of a variadic function. Instead of passing arguments as registers, you pass it on the stack for these certain cases. Okay, so save password to file. Let's focus on some of the stealer stuff. I know we're almost at 5 already, but there's some interesting things that happen here. After it does the password capture, I just want to talk about this really quickly because I think it's really cool. It actually tests your password, and it uses these. I didn't know about these until I was looking into this. Other malware samples, like Atomic Stealer, uses DSCL utility in order to check for the password. But this uses like these old CF core foundation string queries, and it actually authenticates using the password to verify that it actually works. So not only do they capture the password, they make sure it's right, which is pretty cool. And this returns a bool if it's actually the right password. And if it fails, it just keeps prompting. Awesome. So this is where all the stealer stuff happens. Before we get there, this .local -UUID that we created, it also added this password.dat file there. And we see this fopen function for anyone familiar with C and C++. To write to this file. So after it checks that password, it then writes the user's password to this directory, and then it uses that later. So this is the C2 for this sample. It actually passes the C2 to this function and uses it way later. I don't know why they coded it like that. And this is where all the stealer stuff starts to happen. And I think this is fun to look at. So here's some examples of things that it steals from. Wow. Make sure, yeah, there's a couple here that's pretty cool. So FileZilla, for anyone that uses that, you'll see these XML files and FTP related directories. This is it basically creating references to these paths so that it can then target these paths and collect all files within those directories. It actually gets stuff from Steam, which I found this actually, I was looking at how often this happens, and apparently Windows stealers do this. And I was like, oh, that's not nice. So Steam stuff, for some reason, I don't know, getting config files and login user. I haven't really looked at what this file is, but it also grabs that. And then it gets, a lot of these stealers are focused on cryptocurrency. Then we go into all of these different wallets, Ethereum and Electron Cash, Monero. It just looks for all of these wallets based on the normal locations where these files are stored. And then they did their research and they looked for, what files and what directories these things exist and where are the files in their SQLite databases that store specific information about these wallets. And and then
it's a reminder to use cold storage.
These stealers are very good at finding.
They even take your Dogecoin. Damn.
Yeah, everything is in here. Like they just throw everything at it. So that's for that. It goes into Discord and gets all your Discord stuff going into the local storage. Telegram as well. And it actually grabs your shell history or ZSH. I don't really see that often on macOS, but that's more of like a Linux thing, I feel. But it does grab that, and it does also query for SSH keys. And after that, it then uses curl. Well, hold on. There's a whole block here before we get into other stuff. Then it sets up curl. This is a function that sets up curl. And it's actually a cool way to set up curl if you're an attacker. Instead of just spawning a new process that runs curl, they actually leverage curl APIs in order to do it, so that, if you have a process monitor type in for specific curl processes in your enterprise, this would slip underneath that because it's using the APIs. So this is not going to spawn that curl process that many orgs look for. So that's pretty cool. It just sets up all these different operations using the curl easy setup for different commands that it runs, like what fields it's going to post and all that. And then that's how it starts to use the C2 to post information outbound. Then it's interesting what they do here. Then it does all that for third party. And then there's an entire section for Apple related stealing that it comes after. So one thing that we didn't really understand when Adam and I were looking at this was why it uses this OSA script to mute the volume from your machine. I don't know why that happens. It's like 1 second, but it looks related to potentially trying to disguise itself as it's attempting to access Apple related files. I don't know if that really works well, but they actually attempt to run that command. You can see it being passed here to the popen function. So, excuse me. Now it does Safari stuff. So it looks at binary cookies and all that good stuff for sessions. And there's been a lot of talk recently about sessions being stolen by info stealers and potentially causing, bad things to happen. So they're looking for things like that too. There's some keychain related captures for the library keychains for the user. It actually uses a specific OSA script for Apple only, which I thought was pretty interesting. So these are more of those capture and related prompts that move files to different locations. And this is actually used quite a bit here. And was this key different? I think this key was different for this XORing. I don't remember. Let me see. Yeah, so even the XOR key is different for these specific calls to the OSA script. So that kind of threw me for a loop. I don't know why they did two different keys, but they were trying to be sneaky. So then it also grabs things from the Notes application. You can see that here. And then it creates this temp dir, and then it grabs all these types of files here. So so text, RTF, docs, docx, all this fun stuff. It also grabs. Yeah, so pretty nasty. And after it finishes all this, it then goes back and this finishes. And then I thought this was interesting. So last thing I'm going to talk about when it comes to this, after it does all this, remember all the way in the past, when we first started talking about this, this is masquerading as a legitimate app. All that we just talked about happens very quickly, right? Computers are fast. So after it does all that, then it looks back into the resources directory, which I don't remember where we are right now. Let me see. So, it was in here. Volumes, and then dump media converter, and then hold on. What is in here? Oh, the app. So that was correct. Content, and then resources. So just to go back, make sure I remember, because I forget a lot. Here we have the actual legit app is inside of this resources directory. So this ends up looking for that application inside of the resources directory, and it moves it into the legit applications directory. And let me see if I can show how it grabs this. Yeah, so it uses these functions. It does a string copy using this cf string get string pointer, copy file system path, copy resource URL. Remember, this is inside of the resource directory inside of the application bundle. So this is using APIs to target and copy the file from that location. And you'll see it. That's the app. This is a CF string. So then it copies that, and it copies it into this applications directory. And how do we know that? It uses this copy.r. And again, it passes in using sprintf. It creates this string that passes in the origination of that file and where it wants to end up. And it copies that to the applications directory. And then it does an open to actually open up the legitimate app. So after it does all this stealing, all this horrible stuff that you don't want, then it graciously opens up the app that you downloaded for some reason, and you would not know unless you were alerted to something. So pretty sneaky. There's been another version of this that came out recently. Another researcher named Alden, he's at Huntress. He found one that actually looks like Brew. It installs very similar to Brew for anyone that's that uses macOS. Homebrew is a very common thing that a lot of people end up installing immediately when they get their machine. So they created a site that looks like Homebrew, and it actually has that command that you copy paste into your terminal, and it downloads this sample and it runs, and then it attempts to masquerade as Homebrew, which I think is more potentially interesting because I don't know how many people are actually going to go out and download this Spotify converter app, but I know a lot of folks that use Homebrew. So that shows that the authors are trying to pay attention to what users would most likely download and install and use. And they're using that for their lures, which is pretty cool. Or not good, but it's interesting to reverse engineer. Okay. Where are we on time? It's 5 o'clock.
Yep. It's up to you. I mean, if you want to go a little bit longer, you can. Otherwise, if you got to bail, I totally get it. It's been awesome so far.
Let's see what else I wanted to talk about.
Trojans, man, old as time itself.
Yeah. Oh, I'll do quick thing. This kind of a sneak peek, which I think is fun, just to save this for the end. This is going to hopefully be a blog post that goes out soon because it's a new variant of something that we've been looking at for a while. I mentioned atomic stealer. This is another stealer, and it does. I don't know why it does this, but let's just talk about it very quickly, and then we're done after that. So really quick, we're going to go back to this directory. Actually, I think I already have it. Yeah, I already have it. So I don't need to look at the file itself. Open and this one. Okay. This is C++, which you said that you're a C++ person.
Yep.
I cannot stand reverse engineering C++. It's not fun.
Browsers and the kernel have been my life, so yeah.
It can be very annoying. But let's kind of walk through this really quickly because I think it's interesting enough to talk about. So we're inside of the main function for this other stealer, and it has this decodes function, which is an actual function that they named, the malware authors. It's one of the symbols in here, and you can see that it takes in a string. But what does it do? So it took me a while looking at this to try to figure out exactly what it does because it's not immediately obvious. So this actually uses base 64, and let's show how that works. So we need to go into this assembly because it's a lot easier to see it. So we're going to go where this is. So here is a hint of how this works. So we have a call to memcopy to copy over some value to a memory location. We have a decodes function, and then we have a call to system, which executes what this is. So that immediately tells me this is going to be our string that's going to get decoded, and it's going to be passed into system as a command. And the system function takes in a string command. Okay, so how do we know that this is base 64? So let's just kind of walk through this really quickly. This string is loaded into X1. Let's take a look at this. It's gigantic. Very, very, very large command that we're going to find out what it is and how it works. That's into X1. We move this value into W19. We're not really worried about that just yet. And then we move W to this value. All right. So if you know what the memcopy function is, you already know what this is doing. And yes, man pages and API docs are your friend. So this is the destination is going to be X0. This is going to be X1. And our size is going to be X2, the third argument. So this is our size. That's passed in. So that's a huge string. All right, so what is that? 24,000 bytes. It's kind of ridiculous, but that's what it is. Yeah. And then X0 is this value here. So I sometimes go the other way, right? So like you look at something interesting. This is just a reverse engineering thing that I've picked up and I've seen other people talk about it too. All right, this call system, how does this work? You go up. Oh, this decodes something. What does it decode? You go up. Oh, this calls memcopy. How does memcopy work? It moves this value to this, or this thing from this location to this memory address. Okay, so what is used as the argument to that? X0 is our destination. And this was stored here. So this is our string. So what is X0? X0 was returned by this operator new. What is that? In C++, that's like a malloc from what I remember.
Yep.
Mu would be a malloc, and we passed in the size here. So this is like, just for my C mind malloc, we passed in the value 0x5fb0. So that's the size of the heap the heap pointer that we returned into x0, and this heap pointer was stored here. So this memcopy stores this string that is 24,000 bytes in length at this address. And how do we know that this is passed into the decodes function? Because we move that stack pointer, which again, we stored it on the stack at SP here. We moved that way. And then before we called this decodes function, we moved it back into X0. And then
it's after 5, bro.
Yeah, my dog's like, goodness, you gotta get out of here. It's gonna be real fast. So how do we know it's base 64? Well, we see a call to these base 64 character values, right? So what is this? If we look for where else this is called, we'll see that this address is part of this static initializer inside of the main.cpp file. And so this is run or set up when you create a static variable. This is executed prior to main. So this ends up putting in these characters as the variable for the base 64 characters that are used by this function. So this is, if you see this and you've reverse engineered stuff like this before, you immediately feel like, oh, that's base 64 that they're using. So this is how you know that it's using base 64. So then that returns. So last thing, just to show how this works, we know how this works now, right? So it's going to decode that function. It's going to be passed into this. So what is this in base once we decode it? So we can just run something really quickly for that, for fun. So this is the address of this string. We're passing in the length because Binary Ninja has this function that you can run, which allows you to read a certain amount of bytes from a certain address for a certain length. And we're going to just use this base 64 library to decode it. So I'm converting the bytes to a string, decoding that. And then this is our gigantic command. And you'll see in here a bunch of wallets, Microsoft Edge stuff, and all that fun stuff that looks similar to what we were seeing in another sample. This is a separate sample, but another stealer that steals a bunch of information from the system. And it uses base 64 because this looks like gibberish to a lot of engines out there that are looking for malicious samples. Okay, I think we made it.
Yeah, that was awesome, man. Very, very well explained.
Cool.
We're too big now. Whoa, there we go. Back off. I don't like it when it's full screen like that. Yeah, that's awesome. Do you teach for anyone or for yourself or?
No. I mean, I'm a parent, so maybe that's helped.
I'm gonna bug you then because you're awesome.
Oh, awesome.
Yeah, I've got 1,200 people on, so definitely people are interested in this. So it's great.
Cool. Yeah. What we said at the top, just want to say, anyone that's interested in macOS malware, go to that GitHub page, go to Objective-C blog, and just start looking at malware. And it's how I learned. It's a great resource.
Yeah, great pointer. So I know you got to go, so we won't take any questions right now. Sorry about that, folks. I know some people had some questions go by, but if you want, go ahead and post the questions up on the actual YouTube as a comment, and then I'll hit up Chris to go and say, hey, take a look at that, and maybe you can respond to folks if you don't mind.
One last thing, I'm putting in a link to our blog where I talked about the cuckoo sample at InfoStealer. For anyone that wants to dive into more of how that works, This sample was also uploaded to Objective-C GitHub. So that's another one that you can follow along, look at the blog, and reverse engineer it.
Nice, cool. I posted that up, and let me post up one more time your Twitter link there, so folks can follow you. But great, I appreciate it, man. It was great having you on. Love to have you back on again. I know folks enjoyed this, so thanks again, and everybody have a great weekend. Any final words for you? I guess you already said your final words, Chris.
No, this was fun. I love talking about this stuff, and ARM is beautiful. So take the time to learn it.
It's hard for people to switch from x86, 64, but so awesome, man. Well, again, everybody have a great weekend, and thanks so much. This is a great stream, and we will see you next Friday at 11 a.m. We're going to be taking a look at fuzzing with source. Source is the handle of the individual coming to present. So next Friday is fuzzing, and we will see you all next time.